All right, Bio 400 A block. We're going to be talking about something called chemiosmosis. And you should know that osmosis is something we've worked with. Oh boy, that's... Let me... Sheesh. And it's a familiar term to you. If you recall, it's the movement of water through a selectively permeable membrane. Well, instead of being water, we're going to move a chemical. And specifically, in our case, the chemical is going to be protons. Now, don't forget that protons are really a hydrogen atom that have lost their electron. And so they just become this positively charged hydrogen. All right? And I'm going to refer to them as protons because that's all they consist of. It's just the proton. No electron, just the proton and a neutron. All right, now, before we do this, let me provide for you a metaphor for understanding this concept. And it's worth taking these notes down. Imagine you have a hydroelectric dam. Now, many of you probably have no idea what a hydroelectric dam is. So let me just go ahead and build this thing. What you do is you take a river and you dam it up so that all the water builds up on one side upstream of this dam, and it creates, instead of a stream, a flowing river, it actually creates a lake. So you have this giant lake of water. And what you may not realize is that in this dam here, there's actually a tunnel through which water can flow. But rather than just letting the water flow willy-nilly however it wants to, there's a propeller of sorts that's hanging out here. And that propeller is attached to a generator. And a generator then produces electricity that will then flow out of here. And electricity essentially is electrons flowing along a wire. And ultimately, it sends this electricity through these big towers, and it runs all the way to the city to light up, or the town or whatever it is, to light up or provide the electricity needs for that particular city or town. Now, the way this works is that you need to have the water flow through this tunnel, thereby spinning this turbine here. Alright, so let me just unlock this so we can get closer in here. That turbine spinning, which is again attached to this generator here, is what causes the flow of electrons. And then the water scoots out, goes downhill, and essentially forms a small trickle of water, a small stream that will exit and continue along its way. Alright, so the movement of the water in this case is what provides the energy to do the work. But it has to have this lake built up over here. If you don't have this lake of potential energy, you're not going to have a flow. So for example, let's say we have water on both sides of this dam. Let's say it's a massive flood and we have water on both sides of the dam. Well, the water's not going to be encouraged to move in this direction, right? It's not going to be cruising out through here because there's no potential energy. There's no difference in potential energy that exists on either side of this dam. You really have to make sure that you get rid of this so that we always have that constant flow of water. Alright, so why do you think this is important? Well, as it turns out, if you recall, going back to our chloroplast, if we're going back into our chloroplast and looking at a thylakoid, okay, so here's one of those thylakoid discs, alright, and I'll just draw another set of them going down here. So we have the stroma out here. We have the interior of the thylakoid membrane system going on right here. And then if you recall, very importantly, we have an electron transport system. And let's say over here, we have, let me just erase this bit here, a ATP synthase with a tunnel. Okay? And it's very important that you recall that somewhere along, well, actually, hold on a second. Let me zoom in on this for you. So let's zoom in here. Right along, say, right here, we have a place where an ADP molecule and an inorganic phosphate, PI, will actually attach itself there. But don't forget, if we go back to a few screencasts ago, to bind ADP to P sub I, you need energy. And it turns it into ATP, which is the energized form of the molecule. But you need energy. Now, it just so happens we have this great setup here. Because if you recall, we have just in front of this electron transport system, we have a photosystem. And in this case, the photosystem we worry about here is photosystem 2. And along photosystem 2, somewhere along here, there's a spot for, I'm just going to draw it in black here, spot here for a water molecule. So water, which comes from the soil, up through the xylem vessels from the roots, up through the xylem vessels, and into the leaves, and then into the palisade mesophyll of those leaves, and specifically into the thylakoid membrane system to photosystem 1, you find this water, and it's in liquid form, that finds itself snuggling right into that photosystem. It finds a specific spot there, and in that spot, let me just, in this spot here, we have a process that you saw today, learned about today, called photolysis. Okay? So we have photolysis of water that takes place right there. Now, photolysis is a cool word because it actually says exactly what it's doing. Photo having to do with light, lysis cutting. So sunlight, in this case, it's a photon of light, will actually cut up the water molecule. Okay? And in fact, it breaks up the water molecule in this very specific way. You take the water, you undergo photolysis with light, all right? And as a result, you end up with protons, with electrons, and with oxygen. Now you know the oxygen just sort of scoots out of the thylakoid membrane system through the stroma, out of the chloroplast, out of the cell, and eventually will make its way out of the stomata and into the air, into the atmosphere. But those protons and electrons are going to be very important things. Okay? The electron, I will tell you about the fate of the electron tomorrow, but it's that proton that's important, because what happens here is the protons, because of the photolysis of water, begin to build up inside the thylakoid membrane system as a result of the photolysis of water. I'm going to erase a few things for myself just because I want to be able to put some more things in here. So, but you probably shouldn't do that. You should keep it all there intact. So I have my protons building up. Lots of photolysis is going on here. And very importantly, the result of this is that you begin to develop a gradient between the thylakoid membrane system and the stroma with respect to the protons. So you have a high concentration of protons on this side, and you have a low concentration of protons on this side. This is not unlike what we have going on here. You have a lot of water over here, no water over here. Now, of course, this isn't water we're talking about. We're talking about protons in this case because this is not a hydroelectric dam. And so if you have this concentration and you think of this ATP synthetase as being sort of like the hole in the dam that allows for the flow of some water, not all, but some of the water, well, that's exactly what's going to happen here. These protons will actually scoot through here. Okay, so every single one of these protons is going to, actually that's not true. Most of these protons are going to find themselves scooting right through one of the many ATP synthases which are covering this thylakoid membrane system, or the seta grana. And as they cruise through there, their flow actually creates enough energy to bind together the ADP and the P sub I, and as a result, create ATP. Just in the same way that we saw the flow of water spun the turbine to create energy that is then moved to your homes to light your house. In this case, it's not electricity that's generated, it's ATP that's generated as the protons go scooting through there. Now here's the problem. You can imagine that at some point this is going to lead to having protons out here. Right? And if it's a concentration gradient, things are always moved from an area of high concentration to an area of low concentration. So for every one of these dudes that I move through, right? So let's say if I erase, if I erase this dude, and this dude, then I'm going to have to add those three out here. And at some point, you're going to have the same number of protons on either side of the thylakoid membrane system and the stroma. And that is not going to encourage the flow of protons, which means you're going to stop creating ATP. It's just like what I showed before when I showed you guys a situation where there was a major flood and you had water on both sides of the hydroelectric dam. It meant that there was no way that water was going to continue to flow through that turbine and generate electricity. Well, the same thing here. Protons on both sides, an even amount. We no longer have a concentration difference, right? So I can't have that in here. The concentration is going to be the same. It'll be isotonic on either side. That's a bad situation. The plant actually is going to be very unhappy if that were the case. But in fact, that isn't the case. Oops. I don't know why I said redo there. Sorry, let me erase that again. What happens here is that those protons do two things. Some of them get used in the process of making NADPH. Don't forget that NADPH takes an NAD plus, let me just write that, NADP plus, plus protons plus electrons. That goes into making an NADPH. So some of the protons are clearly going to be consumed in that process. But that doesn't account for it. You can't just rely on NADPH making. You need to have a much greater difference. All right? So that's some of it, but that's not all of it. So let me go ahead and erase those dudes. Whoops. Okay. If you recall that there is an electron transport system right here, right, that follows after photosystem 2. Well, that electron transport system, I said, is responsible, this goes back to that puzzle that we're putting together, is responsible for moving protons. And in fact, what it does is it moves the protons that are hanging out over here, and it scoots them back into the thylakoid membrane system. Okay? So all these things, and don't forget, there are multiple electron transport systems following photosystem 2. There might be one over here. There might be one over here, over here, over here. So that means there's a lot of work going on here where the electron that was formed from the release of the electron from P680 that went flying through the electron transport system, that electron was doing work, and the work that it did was to reset the concentration gradient. So we take all the protons that were hanging out here in this area, and we move them back right into here as a result of the action of that electron transport system. So that electron transport system resets the proton gradient, which then will allow us to continuously use ATP synthase to make ATP. That, my friends, is chemiosmosis. Pretty cool, huh? Goodbye.